Hello, this is Team Purple Team. And this is the presentation on the filter wash station, steady state, and step response behaviors. I'm Roger Pierce, and the other people in our team is Randy McCauley, Steven Snyder, and Ross. Sorry, Ross, I can't pronounce it. As you see, this presentation is from the future because I didn't think it was tomorrow. So that's great. All right, an overview of the presentation.
Well, let me show you something right there. That's for everybody. Don't be, you mind if I interrupt you there?
Yes. No, I'm good. No.
Trying to get that date. How do I do that? There you got the date, right?
Yes.
Insert. Somebody help me. I want to insert the date. Where is that? He was just typing the date. That is so 20th century.
I don't know.
Maybe format?
Huh?
Format on the far right.
Format.
Will it always display today's date?
Yeah.
No, that's not it. Always, man.
Design.
It should be on there.
Huh?
It's a lot of words you just talk.
And if you maximize the
Spit
window,
out today's date.
Say it again.
if you maximize the window, sometimes it hides it, like hides certain features.
Insert.
Date time.
Where? Oh, right there. Click on that. And it's a automatically update. Please. And it'll always be the right date. And anybody know how to get the slideshow started? You don't have to go here to slideshow and whatever. You just hit F5. F5 all the time. Just F5. Everybody say F5.
F5.
Now, want me to tell you another trick?
Yes.
All right, so let's say you're looking at this graph here, and down at the bottom it says that's slide 5. And for some reason, you might have worked on this a while, and you might remember that slide 5. So it goes in here, you hit a 5 on the keyboard, and enter, and it goes right to slide 5. And when it goes to the very last slide, type in 99, and if you have less than 99, it will go to the last slide. Back to 5, 5, and go to 2. No, 2. That's where it interrupted you?
Yeah. Now my flow is totally off.
We'll start off, yeah, all right.
Sit back down and start over.
Yeah, sit back down and start over.
Okay. An overview. First, we're going to do some filter wash station background. Then we're going to the steady state operating curve, how we got it, how we calculated, what we got from it. The step response, and then round that up with some conclusions. All right, here's a system schematic. It's a pretty simple system. We have a wash water inlet and a centrifugal pump. And in this control loop, we have a flow transmitter, flow recording controller, and a flow controlling driver. Because it's an AC pump, it controls frequency of the AC voltage. There are two valves that stay open in our experiments. Here's a block diagram. The manipulated variable is input motor power. And in our control variable is the wash water flow in pounds per minute. For the steady state operating curve, first we had to figure out where in the range of 0 to 100 our output area of interest lied, and it was between 10 and 18 pounds per minute. So we did a few initial guesses, and we got it to be somewhere between 30 and 100%. So we did these flow versus time charts with a steady input percentage across that range. And as you can see, there's a small transient portion that we didn't care about, and then it goes into this steady state. And for this particular 80% input, it ended up being an average of 17 pounds per minute, low standard deviation of 0.3 pounds per minute, which would correspond to an uncertainty of 0.5 pounds per minute, two standard deviations. All right. Do that a bunch of times, and you're able to construct the filter wash station steady state operating curve. As you see, it goes from 30 to about 95%, and it's fairly linear. It does kind of go away from the slope that is present here, but what I did was I drew a line and kind of got a graphical method for getting the slopes, so I wasn't able to use the trend line. It's about 0.1 pounds per minute per input percentage. And that actually corresponds to our system gain. And also at the bottom, this is how we divided up the areas into very low, low mid, high mid, and very high for we did step response. All right. And for step response, we set it up to be, in this particular case, at 40 seconds to go down 10%. As you see here, we zoomed in and we compiled a bunch of these. We did 3 trials up and 3 trials down, and we employed graphical methods to get tau, gain, and dead time. And I didn't want to clutter up this graph with those lines, but we'll get to that. Results from the step response. The blue bars are the gain if we went up, and the red ones are the gain if we went down, and we have uncertainty bars on this graph. And you can see that the gain actually decreases as we go up the range, and that actually corresponds fairly well to what happens on the steady state curve. Steady state operating curve, the slope kind of goes down. Dead time, we represent this in the same way. It's a graphical method, so people get a little slightly different answers as far as what the dead time is. Again, blue is up and red is down, and it doesn't seem to actually trend in any direction. So we actually just took the average of all of these. Tau, same presentation. Most of us got a higher tau when the step is going up than down. Randy was the odd man out on that. Sorry, Randy. Okay. And if we compile all this information in a simple slide, I hope you get what we did. The operating range was between 30 and 95%. The output was from 10 to 18 pounds per minute with an uncertainty of 0.5 pounds per minute. And the transfer function parameters from the step response, a gain of 0.1 pounds per minute per input percentage with an uncertainty of 0.01. The dead time, 0.4 with an uncertainty of 0.1 seconds. And the time constant, 0.8 plus or minus 0.3 seconds. And now it had the highest uncertainty because we all kind of got different answers for that. It's a graphical method.